Shocking discovery. Electrons blasting away from the sun at nearly light speed have finally been traced back to their explosive origins. But here's where it gets controversial. For years, the spotlight fell squarely on solar flares, yet fresh data insists that colossal coronal mass ejections, CMEs, play an equally vital, even overlooked, role in hurling these energetic particles into space. Since its 2020 launch, a joint ESA-NASA Solar Orbiter mission has ventured closer to our star than any imaging spacecraft before, carrying a suite of 10 instruments designed to capture solar energetic electrons, SEEs, in their earliest, pristine state. By sampling hundreds of these high-energy events at distances ranging from about 40 million to over 150 million kilometers from the sun, the mission team has for the first time pieced together a comprehensive picture of where these electrons really come from. It turns out there are two distinct electron families speeding outward. The first, dubbed impulsive events, erupts almost instantaneously in tight bursts linked to solar flares, sudden bright flashes on the sun's surface that release radiation across the spectrum. These electrons are like sparks from miniature fireworks clusters, launched from compact active regions. The second family follows a different script. As massive CMEs, vast bubbles of plasma threaded with magnetic fields lift off from the corona. They gradually liberate energetic electrons over hours or even days. These gradual SEEs escape not in a single burst, but in an extended swell of particles, akin to a rolling wave rather than a pop. And this is the part most people miss. Once unleashed, electrons don't zip straight to our detectors. They travel through the solar wind, a constant gale of charged particles that drags the sun's magnetic field outward, bouncing off turbulent eddies and twisting field lines. Laura Rodriguez-Garcia, an ESA research fellow, explains that this scattering can introduce significant detection delays, making it tricky to distinguish a genuine release lag from the time electrons spend wandering through interplanetary space. Why does all this matter? High-energy electrons, especially those tied to CMEs, can damage satellite electronics, interfere with radio communications, and pose radiation hazards for astronauts. In February 2022, a geomagnetic storm driven by a CME knocked out up to 40 of SpaceX's Starlink satellites, costing the company tens of millions of dollars. By clearly separating impulsive and gradual CEEs, space weather forecasters can better predict when and how to shield spacecraft and protect crews on orbit. We could only untangle these two electron populations by measuring particles close to their launch point before the solar wind scrambled them, says team leader Alexander Wormuth of the Leibniz Institute for Astrophysics Potsdam. Daniel Mueller, ESA Solar Orbiter project scientist, adds that the unprecedented database of early-state SEE events amassed over 5 years is now available to the worldwide research community. Looking to the future, ESA's SMILE mission, set to launch in 2026, will map how the solar wind interacts with Earth's magnetosphere, offering fresh context for SEE propagation. Then, in 2031, the Vigil spacecraft will station itself at a vantage point that peers around the sun's far side, giving us early warning of flares and CMEs before they rotate into view. The team's analysis was published on September 1st in Astronomy Astrophysics. So, here's my bold question to you. Are solar flares really the main villains of space weather, or should CMEs shoulder more of the blame? Could it be that previous models have downplayed the CME contribution? And what does that mean for how we protect satellites and astronauts? Do you agree with this new interpretation, or do you see alternative explanations? Share your thoughts and spark the debate.